Hi, so in this video we're going to continue our discussion of phase plane analysis for systems of two autonomous first order differential equations. And the focus in section 6.4 of Edwards-Penny is mechanical systems, so those are second order differential equations and the corresponding first order system. So, as you know, the lecture notes that I'm working off of, both unfilled in and filled in, are posted at our lecture page. And I'm planning to put video links on that page corresponding to the lectures for the calendar day and topics. So that'll be our special playlist. All right, so for a warm-up exercise, this is something you should be able to do, remember in chapter 3 we talked about the pendulum, which in chapter 3 we were doing small oscillations, but now we're going to turn that string that the mass was hanging on into a rigid rod, and it's going to be able to go around any angle theta. In fact, it could be swinging back and forth, or if the velocity, which turns out to be L theta prime, is big enough, then it could be going around and around and around. So we're going to rederive the second order differential equation for that on the next page. And if you want to, you could stop right now and go to the second page and rederive it there. Okay, so here's how it goes. This was the configuration. The length of our massless rigid rod is L, and there's a free hinge. Well, it's attached, I don't know what the right terminology is, so that this thing could go around and around and around, or it could swing back and forth. So let's figure out the differential equation, and this is a conservative system because we're assuming at this point that there's no drag. And so the total energy, which is the kinetic energy plus the potential energy, is constant on any solution trajectory, or any solution function here. So let's write down the total energy. So the only kinetic energy in this, because the rod is massless, is 1/2 mv squared, where v is the scalar velocity of the ball that's following a circular arc. And the potential energy from gravity is mgh, where h is the height measured from any fixed point, and to make life simple, we'll choose that point to be the lowest point that the mass can be, so when it's at the bottom. All right, so now let's figure out what these are. So remember, what we meant by the scalar velocity v was if you measure the arc length s of t, oriented so that when you're going counterclockwise it's positive, so s of t could be positive or negative, then v was s prime of t. Now what was s of t? Well, from sector geometry, s of t is L theta of t, where theta is the angle, the oriented angle from the vertical, say. The velocity is L theta prime of t. Okay, so here we go. 1/2 m L squared theta prime of t squared. That's the kinetic energy plus mg. And the height from the bottom is the length of the whole string, which is L minus the length of this string from the vertical location of the mass to the top, and that's L cosine theta. And as long as theta is less than pi halves, that's just good old SOHCAHTOA, but that's actually true as you knew from calculus, even when theta is any angle. Okay, so the height above the bottom is L minus L cosine theta. Okay, cosine theta of t. All right, so the total energy is constant as a function of time if and only if the derivative of the total energy with respect to time is identically 0. So the fact that energy is conserved means that 0, which is TE, I'll suppress the little t's just to save time. So the t derivative of the total energy is, now let's just differentiate it. So it's 1/2 ml squared, that's just a constant factor. And now remember we're differentiating theta prime squared, so that's a secret chain rule where the outside function is the squaring function. Its derivative is 2 times the stuff inside to the first power. And then we have to multiply by the derivative of the stuff inside. And then when we differentiate, and when we compute the time derivative of the potential energy, mgl is a constant, its derivative is 0. So we look at the second term, we get minus mgl. The derivative of cos is minus sine. And then we have to take the derivative of the theta function. Sorry for squashing that all together. All right, so let's factor out the, an ml squared. The half and the 2 cancel. Let's also factor out a theta prime. Then in the first term, we're just left with theta double prime. And in the second term, minus minus is plus. So I've got a g. I only had an L in the second term, so I have to divide by L here because I have an L squared on the outside, and I get sine theta. Okay, so that's identically equal to 0 on any for any solution function, and this is true for all solution functions. And theta prime is essentially a free parameter because you can set this in motion at any time with any initial velocity. So the theta prime should be thought of as a free parameter as you look through families of solutions. So the differential equation has to be that theta prime prime plus g over L sine theta is the zero function. And I'm sure you remember in chapter 3, for small oscillations, we linearized sine theta to theta, and therefore, and for that harmonic oscillator, the angular frequency omega naught was the square root of g over L. Okay, so now we're going to stick with the nonlinear function. Okay. So let's look for constant solutions. This is an autonomous second order differential equation, and constant solutions have theta double prime equal to 0, so it must be that the g over L sine theta is 0, so it must be that sine of theta is 0. And so theta must be a multiple of pi. In other words, the mass is either resting at the bottom or it's all the way at the top, so that it's L units directly above the hinge. And it'll be at the bottom when theta is an even multiple of pi, because we were measuring theta from the bottom. And it'll be at the top if theta is an odd multiple of pi. And obviously, we expect the constant solution at the bottom to be a stable constant solution, and we expect the one at the top to be unstable. It turns out the easiest way to make sense of this is to convert the second order differential equation to a first order system, which we've been doing a lot, and you might want to stop right now and check that the second order differential equation is equivalent to the first order system here. And or you could watch me remind you. Remember, we just looked for the system that theta theta prime solved. And so if we take theta theta prime and compute its t derivative, in other words, we're taking the derivative of each function inside the vector, well, we're starting with, in this conversion, a solution to the second order differential equation. So theta double prime is minus g over L sine theta of t. In other words, for the pair theta theta prime, we have that x prime y prime, well, x prime is theta prime, which was y, and y prime was theta double prime, which was minus g over L theta, which is x. And remember, we can go both ways with this equivalence. If we start with solutions to the first order system, dE2, then the first component function, x of t, will solve the second order differential equation, dE1. Okay, and so this correspondence means that equilibrium points will correspond as well. So if we look for constant solutions of the system, then x prime and y prime are 0, so the f of xy and the g of xy are 0, so we do the usual process of finding the x star y stars that make f and g 0, and if you look at f, it's just y, so the y star has to be 0, and if you look at the g, it's minus g over L sine x, so sine of x has to be 0. In other words, x has to be an integer multiple of pi, and y has to be 0, right? Well, and remember, y came from theta prime, and we're talking about constant solutions, so we kind of knew that already. All right, and so these exactly correspond to the constant solutions of the second order differential equation. And so this illustrates a general fact, which is that equilibrium points and stability definitions and understanding for autonomous differential equations of any order, or even systems of autonomous differential equations of any order, since they always have to do with constant solutions, you can convert those DEs or systems to first order DEs, and that's the place where you do the analysis. Okay, so let's make this concrete. Here is a phase portrait for the first order system. And the coefficient of sine x is supposed to be minus g over L. So we've just picked g over L to be 1, in which case in the metric system the rod would have length about 9.8 meters. But actually you can choose whatever units you want, so this is not really any loss of generality. So let's find the equilibrium points. We already found the equilibrium points. It didn't matter what g over L was. It was always x star y star equals n pi 0. And those are the red points in this picture. I'll just make them a little bit bigger to emphasize. Okay, so that's 1A. Now let's see what's going on with the solution trajectories, and it's kind of a pretty picture. So remember that the x and the y correspond to theta and theta prime. This isn't where my real origin is. The real origin is at 0, 0, which is right in the middle of the picture. But, so if I am up here, you can see that theta of t is always increasing and theta prime is oscillating, and that's totally what you expect, which if your pendulum is going around and around counterclockwise with enough velocity, so with the velocity positive enough so that it can keep going around and around instead of swinging back and forth. So let's write the pendulum motion. Here is around and around. in the positive theta, I'll say counterclockwise, which is the positive theta direction. Okay, in this region, and we've seen this picture before, the pendulum is just swinging back and forth. So here we're calling the bottom angle 2 pi instead of 0, but the theta is changing, oscillating between to the right of 2 pi and to the left of 2 pi, and the theta prime, which is the vertical coordinate, is, remember this is really theta equals 0 up here, is going positive and negative as well. So here this is back and forth. There's an interesting light blue curve that separates those regions, and those are the separatrices or stable and unstable orbits that come out of the equilibrium points at odd multiples of pi. And if you think about it, what's happening there is it's possible to set that pendulum in motion so that it, starting at the top, for example, well, no, so starting maybe at the bottom with just enough velocity so that the pendulum gets to the top, which is in this picture theta equals pi, just as theta prime, well, actually in the limit as theta prime goes to 0, and it came from, if you go backwards in time, it came from theta equals negative pi. As you go back, t goes back to minus infinity. Okay, and as you can figure out, down here, it's around and around, and so it's, I'll say, circling, and it's clockwise, because theta is steadily decreasing and theta prime is oscillating. And if you look at the picture more closely, you'll see that on any solution trajectory in the round and around regions, the theta prime, the absolute value of the theta prime is the smallest when the pendulum is at an odd multiple of pi. In other words, the pendulum is at the top. And that's because of conservation of energy. The total energy is constant. The total energy is constant. And that means that when the theta prime is 0, the cosine of theta t is the most negative, so that the L minus L cosine of theta of t is as big as it can be. I shouldn't have said it that way, but oh well. Anyway, at the top, the velocity is the smallest, so the potential energy is the largest. That's what I meant to say. Okay, so what else were we supposed to do? We did 1B. Now let's just eyeball the equilibrium points. and classify them. And we're really good at that by now. So it certainly looks like the energy minimizing equilibrium points when x star equals n pi, where n is even, when the mass is at the bottom, those sure they sure look stable. They look like stable centers. And the x star equals, well, let's just say n pi 0 when n is odd sure look like saddle points. And you can even see the eigenspaces for the linearization in the picture. Okay, so we did that. For the ones, yeah, so we've been emphasizing that when the linearization is a stable center, that's borderline. And just like in the last lecture, in this example, we're going to use, actually we'll use the total energy function, but in your homework, you'll use separable differential equations to figure out a function which is conserved along solution trajectories, and it'll turn out to be a multiple of the total energy function. Okay, so let's do the linearization analysis and see what we get. It better be what the picture told us. When you're in higher dimensions, you don't have pictures. So and lots of interesting problems happen in higher dimensions. So you have to know how to do linearization. Okay, so we want the Jacobian matrix. And we're first going to just compute it at xy. So it's the matrix of partial derivatives. So the partial derivative of f of xy equals y with respect to x is 0. With respect to y, it's 1. The partial derivative of g of xy with respect to x is minus g over L cosine x. And its partial with respect to y is 0. Okay, so let's do the linearization at n pi 0, where n is even. So we need the matrix for the linear system, u prime, v prime. So that's the Jacobian matrix at n pi 0, where n is even. So when n is even, cosine of n pi is plus 1, so we get minus g over L in that entry. And so the determinant of j minus lambda I, just visualize putting negative lambdas in the diagonal, is lambda squared plus g over L, and so the roots are lambda equals plus or minus I root g over L. So for the linearization, this is exactly when we get stable center. At the origin of the UV plane, which corresponded to the equilibrium point in the xy plane. So that's borderline, or indeterminate. For the nonlinear equilibrium point. let's do the Jacobian matrix at n pi 0, where n is odd. Well, all that changes from the top of the page is that the cosine of x is now minus 1. So here I get a plus g over L instead of a minus a g over L. So the characteristic polynomial is lambda squared minus g over L, which is lambda minus root g over L times lambda plus root g over L. So the roots, the eigenvalues, are plus or minus root g over L. That's a saddle point for both the linearization at the origin and the nonlinear problem at x star, y star. Okay, so that math is completely consistent with the p-plane picture. Okay, so let's do the borderline case. And we're going to use a conserved energy function to prove that those equilibrium points that look stable are. And in the notes, the conserved energy function we're going to use is the total energy. And if you pull out the right constant factors, the total energy is a multiple of this expression. And the other thing to remember when you're comparing this to what you get in your homework is that total energy is only defined up to a constant because the potential energy has a pre-constant in it depending where you were measuring the height from. So this is what we got when we measured the height from the bottom point. Okay, well, here is a graph of the total energy function in the case where g over L equals 1. And in fact, that total energy function at the origin is 0 because the kinetic energy and the potential energy are 0. And you can see the total energy function has its global minimum, but it's also a strict local minimum at the origin. Whereas when you look at the graph above odd multiples of pi comma 0, that graph has saddle points. Okay, and since the total energy is constant on solution trajectories, the solution trajectories will follow contours of the total energy function. And if you project the contours on the graph down to the xy plane, you recover, without the arrows, you recover the p-plane phase diagram. Without the arrows. Isn't that cool? Okay, and in the last video notes, I explained what calculus, what multivariable calculus theorem you need to make this proof precise. The idea is if you have a strict local minimum or maximum, and if you start on a contour near enough to that equilibrium point, then because it's a strict local maximum, you can't run very far away from the equilibrium point. So if you start close, you stay close. Okay, so that was a long one example. As a slightly different example, let's see what happens when you add damping. So, and we're just adding linear damping here. That's the c theta prime term. So now when we compute theta prime prime for a solution to the second order differential equation, we get theta prime and theta double prime. And because we have a solution, we're using a solution to the second order dE to show we get a solution to a first order system, we replace the theta double prime with what it is according to the dE. So it's minus g over L sine theta minus c theta prime, and calling theta x and theta prime y. That's exactly what we have written down here. Okay, and I have to say, I snuck to school to record and upload this because in the last video that I used at home, when YouTube has a slow internet connection, it seems to compress the video more to penalize you for taking so much time to upload it. So you probably can't see the system in p-plane. So g over L is 1, as before, and then the damping coefficient is minus 0.1. So in this one, it's a really small damping coefficient. And isn't that a beautiful picture? So you could do the linearization for small enough damping coefficient, and you could verify that at, in this case, when c is 0.1, at n pi 0 with n even, what you have is spiral sinks. Which are asymptotically stable. And there's other cool curves here. So if you look at some of these curves, they get trapped. So let's look at, say, a curve like this. So if you go backwards in time, it's coming from something where the theta is always increasing as t increases. But then they can get trapped. And you can see they're going to go around and around and around, and they're going to converge to the origin. And what's really happening is that the pendulum was going around and around, but then at some point it didn't have enough oomph to make it to the next high point, so instead it started going back and forth, and the damping made it go back and forth less and less. And in the limit, as t goes to infinity, it converges to the rest solution, the stable solution at the bottom. And you can see the separatrices coming out of the saddle points as well. Those are the light blue curves, which separate limiting behavior, regions of different limiting behavior. Okay, and in this final slide, the damping coefficient is 3. Yeah, so we would call this first one an underdamped pendulum. Okay, when the damping coefficient is 3, what you have is at n pi 0, where n is even, have nodal sinks. Which are also asymptotically stable. Oh yeah, I forgot to say what happens when n is odd. You can see it in the picture. You still have saddle points. Damping doesn't take away the saddle point behavior. And the same thing is true down below. If you look carefully at the arrows, you've got some arrows coming in tangent to an eigenspace and other arrows going out. So n odd still gives you saddle points. And all of this is straightforward to verify, either for a specific damping coefficient or for the letter C in different ranges with linearization. Okay, so here is the upshot of the last few lectures. The last 3 lectures, including this one, are about linearization for autonomous first-order systems of differential equation at equilibrium points. And the use of linearization in studying equilibrium point stability near constant solutions. And the linearization procedure doesn't care whether you're in dimension n equals 2 or a much higher dimension, and so it's very useful when you don't have pictures that you can look at. Okay, that's it.